I want to present a friend, not just a colleague, but a friend, is Professor Raşit Turan from Ankara, from Turkey. We know each other since many years. He's an expert and he's the director of the Center for solar energy in Ankara. The name is in Turkish is Gunam. So the Gunam, I think, if I understand, as I asked him once, it's solar energy. Professor Turan, you are here, is it?
I am here, Ahmed.
Yeah. Okay, thank you. So allowed me to present some detail in Arabic, because we are targeting Arabic people, Arabic world, and we want to do this by courtesy. So السلام عليكم ورحمة الله تعالى وبركاته. سأقدم لكم الأستاذ رشيد توران، الأستاذ في جامعة الشرق الأوسط التقنية بأنقرة، وفي نفس الوقت هو مدير مركز أبحاث الطاقة الشمسية والتطبيقات أنقرة تركيا. سيتحدث على موضوع مهم جدا. أتمنى أنني الترجمة كانت جيدة. تقنيات غير متجانسة مع مختلف الطبقات الانتقائية للثقوب والإلكترونات. عندما تتحدث عن شبه المواصلات semiconductors وتسلط الضوء على هذه المادة بيكون عندك إلكترون and هولز، والهولز بنسميه الثقوب. هذه التكنولوجيا التي تعتمد على السيليكون البلوري لصناعة الخلايا الشمسية هيمنت على سوق الوحدات الشمسية الكهروضوئية بنسبة تزيد عن 95 نسبة مئوية مقارنة بتقنيات الأغشية الرقيقة. وبالتالي أصبح السيليكون البلوري هو العنصر الأساسي في تصنيع الخلايا الشمسية التي حققت خطوات متقدمة جدا من حيث عائد التحويل وانخفاض الأسعار، بحيث تم انخفاض سعر الكيلووات ساعة بعشرات مرات. هذا يرجع إلى تصنيع كمية كبيرة the economy of scale أدى إلى تخفيض النفقات ومعها تكلفة الإنتاج. والأهم من ذلك هو الاستثمار والتقدم في البحث والتطور. ففيزياء أشباه المواصلات semiconductors بالأدلة والتقنيات والتجربة أصبح التحكم في المقاومة الكهربائية the resistance of the doping بلغة أخرى منذ تطوير ترانزستور، وأيضا ضبط العديد من الخصائص. A lot of semiconductor properties are now controlled. البحث والتطوير في الأجهزة الضوئية والفوتونية مكن من فهم وتحسين عملية تحويل كمية الفوتونات وتحكم في امتصاص الضوء absorption، وآليات توليد الإلكترونات الحرة والثقوب generation المرتبطة. كل هذا جعل تحويل الطاقة الشمسية لإنتاج التيار والجهد الكهربائي current and voltage مفهومة بعمق، والانتقال إلى التكنولوجيا واضح. لكن however هناك تحديات عندما نريد استخدام الخلايا الشمسية الكهروضوئية في مناخ صحراوي. الأول هو تدهور الأداء مع زيادة درجة الحرارة، والثاني هو تأثير الغبار الذي ينتشر على الألواح. يبدو أن مشكلة درجة الحرارة قد تم حلها مع وصول تقنية جديدة بجمع نوعين من السيليكون، وهما السيليكون المتبلور كريستالين سيليكون والسيليكون الغير متبلور amorphous سيليكون. البحث والتطوير جعل هذه التكنولوجيا تخترق السوق the penetration of the market وتعد باناسونيك، وهنا لا أريد أن أتحدث على باراسونيك، لكن كانت يعني the company has the merit to be one of the first. باراسونيك واحدة من أكثر شركات تكنولوجيا في تكنولوجيا الطاقة الشمسية موثوقية لهذا النوع. Panasonic is the one of the best, in my opinion, companies. They use this kind of solar cell, combining amorphous and crystalline. تعود تجربة باناسونيك إلى السبعينات من القرن الماضي، عندما تم تطوير وحداتها وبيعها تحت اسم العلامة التجارية سانيو. كان قبل سانيو. هذه الخلايا الشمسية الغير المتجانسة القائمة على السيليكون هي موضوع ساخن، والسيد الأستاذ رشيد توران سيتحدث عن هذا بدقة، فنشكره جزيل الشكر. الأستاذ في جامعة الشرق الأوسط التقنية ومدير مركز أبحاث الطاقة الشمسية والتطبيقية بأنقرة تركيا، لإعطاء المحاضرة الرئيسية حول هذا الموضوع المهم. قمت بزيارة مختبره حيث يقوم بتطوير هذه الخلية الشمسية غير المتجانسة من مفهوم الذرة إلى الجهاز. هو بيعمل fundamental research، البحث الأساسي to the industry product. إنه يعمل بالقرب من الصناعة، فهو أحد الخبراء في تطوير الخلايا الشمسية للبيئة الصحراوية. وصل أداء الخلايا الشمسية من هذا النوع إلى كفاءة قياسية تزيد عن 25%. Professor Turan Raşit, I want to thank you very much for being with us and be patient to give this small speech in Arabic to explain. I think you will do the rest in your talk, and I want to give you the floor.
Thank you very much, Ahmet. It is a very big pleasure for me to be with you today among the friends. We have had a long-term collaboration with you and with the other scientists and engineers in Morocco. We finished one research project jointly supported by funding agencies in both countries. We have organized several activities together in Qatar and later in Morocco, and we have established a very good ties and connections between two countries. And I hope we can even increase these activities in the future, and we can even come to even more impacts on both countries, technology, science, and other cultural, of course, activities. So again, it's a pleasure for me to be with you, and thank you very much for inviting me today to this very nice activity. I would like to talk about, as probably explained by Professor Ahmet, I would like to talk about heterojunction technologies, solar cell technologies. But before going into the details of the topic, I want to show you some information, or I want to explain who we are, what we are doing in general.
You want to share your slide?
Yeah, I will share it. Just a second. You see it?
Not yet. You have to go downstairs and you see
the
green.
Sorry. Yeah. I know. Of course.
Thank you.
Share, and probably you see now.
Yeah, we start. Yes, fine.
Yes, and it is full screen now.
You have to do it. Not yet. You have to click for full screen. Yes.
Is it
Very
full
good.
screen now?
Yes, yes, yes. Very good.
Okay. Good. Let me also maybe get this laser pointer maybe to show. Okay, the title of this talk and this lecture will be Heterojunction Technologies with Various Hole and Electron Selective Layers. And before that, I want to give you some information about who we are. We are located in Ankara, which is in the center of the country. It's about 300 kilometers from Istanbul. Istanbul is the biggest city. Ankara is the capital of Turkey, as you know. Our campus is just slightly outside the city center of Ankara. You see this view from the air, the campus. We are a kind of American-style campus, and it's a kind of closed campus outside the city. It has been forested by students and staff members through the years, so we have a very nice forest just surrounding our buildings in the campus. It is the Middle East Technical University, which we used to belong until the beginning of this year. And the Middle East Technical University is perhaps the leading technical school, one of the most competitive and leading technical schools in Turkey right now. Okay, the center that I am leading is the Center for Solar Energy Research and Applications. This slide is showing the history in brief. Actually, the first paper about solar cells was published in 1986 from our university. It's a long time ago. But the center of our center was founded in 2009 with some support from the government. We constructed a clean room at the beginning, and then we received a lot of different big projects and support programs from the governments and also funding agencies. And in 2018, we opened a new facility. I will show the details of this facility. And now we have a couple of different laboratories with more than 100 people working on solar cell conversion technologies. We have been part of many different European projects, national projects, and now we are almost recognized as the major research center or national research center in Turkey on solar energy conversion technologies. So here you see two major facilities. One of them is still under construction. Unfortunately, it has not been finished yet, but it will be ready soon, maybe end of this year. Here in the building on the left side, this is called METU Research Park Complex. In this building, we will have a large lab space, a big clean room area, and this building is very close to the technology development region of the campus. So we will be interacting more with the companies and other centers. On the right side, you see our facility, which is fully operational now. In this building, we can fabricate all different types of crystalline silicon solar cells, including these, as you see, aluminum BSF, PERT bifacial cells, IBC, and all others. This is a kind of national center for industrial research activities. So we are expecting to interact more with the companies in this building. So if you look at the inside of this building, you see a complete line for crystalline silicon processing. Here you see these are diffusion furnaces, PECVD furnace. This one is LPCVD. On the back side, you see the wet bench areas where we can do a lot of wet chemistry related processes. This is an ion implantation system and ALD, screen printing. So I mean, you can, this is completely compatible with the industrial solar cells. However, it is also flexible enough to do some fundamental and applied research in this facility. So this is a solar cell that we routinely fabricate for different purposes in our facility. As you see, it is fully compatible with the industrial solar cells, but we can also play with many different things here, materials or design, architecture, etc. So it is also very suitable for doing some industry-related research. And here is the first PERC module produced at our facilities. Okay, when we look at our center in general, we have actually 6 divisions. The largest division is silicon photovoltaics division, and the other one is emerging photovoltaics. Emerging photovoltaic people are trying to synthesize new materials, new devices like perovskite solar cells or organic PV. So they are doing, they are trying to invent something, discover something, synthesize some new materials and devices. And we have a outdoor test platform, which is belonging to the module technology. So the module technology group is also developing very fast, even though, I mean, we have recently started creating this group, this division. There is a power electronic and system group, and we have a thermal power system group, which is related to use of thermal, I mean, the thermal energy generated from the sun. And this division is very much collaborating with the mechanical engineering departments of the universities, and also test and characterization division, where we also serve industry, and we give them services in measurement, characterization, and testing. So this is the summary of our center in Ankara. And I believe that this is kind of unique facility in Turkey, as well as in the whole region. I mean, such a flexible and also comprehensive infrastructure is not available in Turkey, and also in the region, maybe in Eastern Europe and Middle East, and also even in Asia. So we hope to collaborate with all stakeholders in our country, as well as internationally in different countries, and we will be very pleased to do so. Okay, now from now on, I will be talking about more scientific things. This is the outline of my talk. Then I will be giving some introduction to solar cells and also some motivation of our studies. And I will explain the concept of dopant-free passivating contact solar cells. And I will specifically focus on molybdenum oxide as a material, which seems to be very promising material for future applications. And also titanium oxide, titanium dioxide, or titanium oxide. And also I will give you some basic studies that we have performed recently at PINAM about silicon heterojunction solar cells. Okay, let's now start with the definition of or description of the standard solar cell. Here you see the most conventional solar cell structure. Here, the substrate, the absorbing layer is silicon, as you probably know. It is usually P-type silicon. On the front side, we have a very thin N+ emitter created by diffusion of phosphorus from the front side. On the back side, we have screen printed aluminum, and also a region created by diffused aluminum atoms into certain distance from the backside. And here is and it forms a P+ layer. And also on the top, we have an anti-reflective coating, silicon nitride, and also to collect the current generated by the solar radiation, we use silver connections, silver contact on the front side. This is the conventional standard solar cell. And here you see the band structure of this cell, conduction band, valence band, and metals on both sides. We have P+ layer here, which is backside of silicon. And when the incoming photons are absorbed by electrons, they are excited to the conduction band, and they move towards the N region, and holes move towards the P region, to the other side, to the back side of the cell. And then you collect them and you form the current. So here you see the schematics of the solar cell, and you have two, of course, terminals, and electron flow takes place from the front side and then go through the external load. So you generate current and power in this way. The record efficiency for this structure was slightly about 20%. And the major disadvantage in this structure, the low carrier lifetime at the backside, low carrier lifetime due to the high recombination at the backside, because this aluminum silicon interface here is not good for the carriers. They are acting as a high recombination centers, so that you lose the generated electrons and hole pairs due to this recombination. So this is the major drawback of this type of standard traditional solar cell. An excellent alternative to this conventional device structure has been heterojunction solar cells. In the heterojunction solar cells, as probably Dr. Ahmed explained, we combine the advantages of thin films and the crystal silicon. Here again, we use crystal silicon substrate wafer as an absorbing layer, but the PN junctions are formed externally by using thin films, amorphous silicon thin films on both sides. Okay. So on one side, we have P-type amorphous silicon. On the other side, we have N-type amorphous silicon. And electrons, again, move towards the N region after formation by solar radiation. But in between this doped layer and the substrate, we use a very thin intrinsic amorphous silicon, which provides a passivation, which improves the interface quality so that the loss is reduced at the interfaces. Okay. So this is the structure that generates very high efficiency. Actually, the record efficiency is about 25% at the moment. Here you see the band diagram. Here, of course, the region between metal and the substrate, we have an ITO layer. This is indium tin oxide, or some other alternatives can be used here, like zinc oxide, etc. So this layer should be transparent to the light, but it should be very highly conductive to collect the current. So we have high efficiency, very good passivation, and very promising technology. But we have still some disadvantages. So you need extremely good control on the layer thicknesses. This intrinsic layer and also the amorphous doped layers should be controlled in a very well way. And then you need to have you need to have exactly the same thickness values in all different fabrication cycles. Surface cleaning is very critical for the passivation. For a good passivation with intrinsic amorphous silicon, you need very high cleaning, extremely pure surface. So another disadvantage is the contact resistance between silver, ITO, and the amorphous layer. So this needs to be also studied and solved carefully. Of course, another very important disadvantage here, to dope amorphous silicon on both sides, you need extremely toxic gases like phosphine and diborane. Phosphines and diboranes are extremely toxic, and only some amount of these gases may be fatal, may be extremely dangerous for the human health. Okay, silicon heterojunction solar cells can be bifacial, which is also another advantage as shown here. So we have silver fingers on both sides, and there is no complete coverage here, so light can pass through the cell from both sides. So this is an advantage. Another advantage is low temperature fabrication and simple process flow. So the most recent values that people have obtained in terms of efficiencies in the industrial case are the efficiency values 25.26 from Huasan company. Kaneka, Hanergy, NL, and Longi have announced more than 25% efficiency. So it is very interesting to say that, to see that the high efficiency values have been obtained by companies rather than research institutions, which is also showing that the automation and large-scale fabrication capabilities are also important in reaching very high efficiency values. Okay. So another very nice, also maybe the futuristic application of this amorphous, this heterojunction technology is the IBC architecture. In the IBC type of solar cells, both junctions are on the same surface on the backside of the cell. P region and N region are separately fabricated on the backside, and you form the PN junction here completely on the backside. So there is no junction on the front side. There is no metal fingers on the front side. So all light coming onto the surface are passed to the substrate and absorbed by the solar cell. It means that we have higher efficiency. So the record efficiency was obtained by the Japanese company Kaneka. It was 26.6. This is the record efficiency for the whole crystalline silicon industry, not only heterojunction. And Panasonic and Sharp have announced more than 25 efficiencies with this device architecture. Okay, now let me move on to some new ideas. One of the new recently studied and focused concept is dopant-free carrier selective junctions. What does that mean? It means that, first of all, in principle, we do not need any dope layer. We don't need any PN junction actually to collect the carriers. So what you need is a proper bond alignment, bond bending on both sides of the device. So if you can find some materials which provide this bond bending and bond alignment on both sides, so that electrons are repelled or are reflected back from one side and holes are repelled and reflected from the other side as shown here. So if you can identify and use such materials here, then you can have a working solar cells. So you see that there is no doping. It means that you don't need to use these toxic gases to make P junction, P layer and layer. So this is very much advantages, of course. I mean, it's very nice to have such a structure if we can reach high efficiencies. In some cases, you might need some passivation, additional passivation, because these materials may not be good enough for the passivation. What are the candidates for these applications? So here for the electron sides, I mean this side, electron selective junction, we have materials like lithium fluoride, potassium fluoride, magnesium fluoride. For the other side, we have metal oxides like molybdenum oxide, titanium oxide, and vanadium oxide. So these are the candidates, but among them, the most promising ones have been identified as molybdenum oxide and titanium oxide. So I will be focusing on these two materials in the coming slides. So let's look at these materials a little bit in detail. Okay, when you use titanium dioxide or titanium oxide, we have a large barrier on the conduction bands. This is the band showing the band alignment. But the barrier in the conduction band is very small. So the electrons can move towards the or through the titanium oxide layer. Okay, so there is a large band offset. Molybdenum oxide is more interesting. Molybdenum oxide has a large actually work function, so that we have a large barrier for the holes. But at the same time, the conduction band of molybdenum oxide becomes closer to the valence band of silicon. So we call this sometimes broken heterojunctions. So it means that holes here can tunnel through this interface. So they can easily move towards the material. So electrons cannot. So it means that even though we have a large barrier in the valence bands, molybdenum oxide is a good material for hole selective layer. So molybdenum oxide is good for the hole collection, and the titanium dioxide is good for the electron collections. There have been several studies recently. One of them is here, a very recent work published in ACS Energy Letters. So here they use molybdenum oxide on one side and the titanium oxide on the other side. But still they used amorphous silicon for the passivation purposes. These amorphous silicon layers are not doped. However, you need them for the passivation, and the structure is shown here. And on one side you have molybdenum oxide, on the other side you have lithium fluoride, and the efficiency they have reached is about 20%, as you see. Okay, now what are our studies? Let me now look into our studies and show the results to you. One of the important parameters here is the work function of molybdenum oxide. Work function is the distance, as you know, from the Fermi level to the vacuum level of the material. It also determines the alignment with the silicons. So here is your silicon substrate, and on this side we have molybdenum oxide. So we performed a very extensive simulation study, and this work was published later on. In this study, we ran the Silvaco simulation program, and then we obtained these results, as you see. So the efficiency versus the work function. As you see, as the work function increases, the efficiency increases also. Okay, and it is showing that very high efficiencies are possible with this material. So it's very promising material. So the structure here we simulated consists of molybdenum oxide on one side. On the other side, we still have the standard heterojunction N-type made by standard N-type amorphous silicon. Of course, we studied molybdenum oxide very in detail. We looked into the chemistry of the material we fabricated, and we developed a thermal evaporation methodology to fabricate good, uniform, and well-controlled films on silicon. And the thickness can be controlled below 1 nanometer, as you see. And also, in the next step, we looked at the contact resistivity of molybdenum oxide and silicon junction. which is very crucial. I mean, contact resistivity is extremely crucial in the solar cell operation. And here on the table, in this table on the right side, you see the contact resistivity of different combination: gold, molybdenum oxide, P silicon, palladium, silver, etc. And one of the points that I want to attract your attention is the difference between P and N-type substrate. So you see the contact resistivity on N-type substrate is always very high. However, the contact resistivity on P-type silicon can be very low. So you see three numbers here from 3 different studies. One of them is ours. This one is ours. And we see that we have obtained sufficiently good contact resistivity for the solar cell operation. So this was an important study before we fabricate a solar cell. So later on, we fabricated a full area solar cell. But this is not the heterojunction solar cell. On the front side is standard solar cells with phosphorus diffusion, but on the back side we used molybdenum oxide. So the front side is formed by phosphorus diffusion, and backside you see we have no diffusion and no doping at all. The only material we used here is molybdenum oxide. Of course, standard fabrication processes were executed. I mean, the cleaning, texturing, phosphorus diffusion, and rear side was polished, and silicon nitride was deposited on the front side as the anti-reflecting coating, and screen printing and firing processes were performed, and finally on the back side we fabricated 15 nanometer thick molybdenum oxide layer. And this is actually the first large area solar cell demonstrated using this material. And later on, we published this, very recently published this paper in Progress in Photovoltaics. And you see the solar cell results comparing comparing 2 cell structures. One of them is with molybdenum oxide, the other one without molybdenum oxide. And here is you see the external quantum efficiency profiles, and it's clear that the advantage of using molybdenum oxide on the backside is clearly seen from this external quantum efficiency plot. You see these yellow, orange dots are showing the molybdenum oxide results, and they are higher, giving higher current values than the other one, than the reference sample. So the comparison is seen, the comparison of the solar cell parameters is seen here in this table. So we have obtained reasonably good VOC values. Our JSC values are also good, maybe can be improved with some improvements. Field factors can be improved. It is still slightly lower than what we would like to see here. So the efficiency values are seen here. So the molybdenum oxide cell is given higher resistivity than the metal-only junctions on the backside. Of course, here, when we look at the open circuit voltage values, we see that we obtain certain level of passivation. I mean, the VOC is improved with the presence of molybdenum oxide on the backside. We have almost 20 millivolt, enhancement in the open circuit voltage value, which is showing that molybdenum oxide is not excellent material for the passivation, but it is providing some passivation to some extent, which improves the open circuit voltage value. Of course, the short circuit current value needs to be improved, and field factor needs to be. So we believe that this solar cell can be improved to give us an efficiency value close to the 20%. This is standard solar cell, by the way. The front side is a standard one, and there is no, heterojunction on the front side. And later on, we looked at the application on ultra-thin crystalline silicon case. Well, in this case, we obtained very thin silicon wafers by etching, and we obtained silicon, wafers or pieces with the thickness of 22.5 micrometer, and we were able to process them in this structure, as you see. So each square here is representing a thin silicon region. In this study, we looked at different metal oxide layers on the backside. We looked at molybdenum oxide, vanadium oxide, and tungsten oxide. So rest of the fabrication steps are standard silicon solar cell fabrication steps. We have, again, N-type doping on the front side and P-type silicon as an absorber. On the back side, we have only these materials. And again, there is no doping. If you look at the structures more closely, you see we were able to get a conformal coating on the front side, and also on the back side, we have. We are looking at the back side. Sorry, this one is the back side pictures. This is a high resolution TEM image of the same region. So the metal oxide layer is nicely seen here with very sharp interfaces, and there is a silicon oxide layer formation between silicon and tungsten oxide layer, as you see. So after these structural and chemical analysis, we again applied these materials to solar cell fabrication. So we fabricated solar cells and measured them using standard characterization techniques. This table summarizes the results we obtained from these three materials and also from the reference sample with aluminum only. So here, what I can say here, we have obtained the best results with the molybdenum oxide layer. So molybdenum oxide is really promising and superior in the solar cell operation. So we have high current, short circuit current, high fill factor, and high efficiency. However, there are some interesting results also. For instance, vanadium oxide is providing higher VOC values. It means that it is providing higher, better passivation on the backside, which is also something to note, and it may be useful in maybe some different device designs. And the tungsten oxide is giving us the worst results, but still tungsten oxide is better than standard aluminum coating on the backside. Okay, now let me now show some of the details. For instance, the passivation can be identified by measuring the lifetime from these structures, and we fabricated special samples to measure the lifetime in these structures and to understand the surface passivation quality. So the reverse saturation current is identified and measured, which is directly giving us the open circuit voltage values. So as I mentioned already, vanadium oxide is the best in terms of the passivation quality. Okay, let me now move forward. Of course, as I mentioned, the contact resistivity is an important and crucial parameter for the solar cell operation, and we have tested these three materials in terms of their contact resistivity values. Here you see the results. Let me show it here. You see the results here. So these black lines are showing the fill factor, but these red circles are showing the contact resistivity values. So again, we have lowest contact resistivity obtained from the molybdenum oxide case, and this naturally gives us the best fill factor value. So the correlation is seen between the contact resistivity and the fill factor, and the contact resistivity of the vanadium oxide film is the highest, and the fill factor is of course the lowest for this material. So we have all analyzed these materials, and we have obtained this efficiency values for this extremely thin silicon wafer. Of course, there is a room for the development, so we are still working on this, and we need to improve these values to higher values. Okay, and another interesting point in this study is the behavior of the back side of the solar cell in terms of external quantum efficiency, because external quantum efficiency measurements gives us directly the quality, optical and electrical quality of the backside of the solar cell, especially when you focus on the region, on the infrared region in the spectrum measurement. Focusing on them, you can understand which materials are giving us better optical and electrical properties. Okay, here you see that the highest external quantum efficiency is obtained with molybdenum oxide, and the next highest is tungsten oxide and vanadium oxide, and the lowest value is obtained with single aluminum contact on the backside. So this is of course directly correlated with the JSC, the short circuit Acum values. So highest short circuit current is obtained with the molybdenum oxide, as I already mentioned. So this result, I mean, this short circuit current results are strongly correlating with external quantum efficiency values, and also with the reflection measurements. So we don't see the details here, but the reflection with the molybdenum oxide is highest. This is showing that we have very little amount of absorption, parasitic absorption on the backside. Here is showing the experimental total cell reflection. So here we obtain the highest value from the molybdenum oxide, which is, which is of course, it is showing that we are losing some due to the reflection. However, it is also showing that there is very little absorption in the molybdenum oxide layer, which is also good. So the total reflection, which is composed of escape reflection and also the front reflection, is shown here. Again, molybdenum oxide is giving the highest value in here. So this is this can be also proven by the simulation here. As you see in the simulation case, again we have the similar results with the experimental values. Okay, now finally, of course, we would like to look at the absorption in silicon. Okay, so as a result, the total absorption in silicon is highest with molybdenum oxide, which is better than the other oxides here in this study. But when we look at the external quantum efficiency values, we see molybdenum oxide is highest as expected from this simulation. However, wolfram oxide or tungsten oxide is lower than the simulation values. This is due to the poor passivation properties, which is not taken into the account in the simulation. So the passivation of tungsten oxide needs to be improved. So this is quite possible, but we need to study, of course, and we need to look at the different passivation recipes and find out the best methodology to passivate the tungsten oxide layer. Okay, I can go to the next topic, which is the electron selective passivating titanium dioxide or titanium oxide. Up to now, I have been talking on only hole selective layer. Now, the next few slides are about electron selective layer, which is titanium oxide. There have been many studies in literature. You can see the list here. So they have fabricated even solar cells with high efficiencies. And in general, the contact resistivity with titanium oxide is getting higher with increased titanium dioxide thickness. This is maybe expected. So you need to have a good control because over the thickness, because the contact resistivity is extremely important especially in the fill factor of the solar cell. Okay, fabrication of titanium oxide on substrate can be best done by atomic layer deposition. We perform this in our facility. We had an ALD system for this material. Of course, the temperature, post-deposition annealing, film thickness, and the interlayer needs to be optimized. And some of the process parameters have been fixed just to check these 4 parameters in our study. So in this ALD deposition of titanium dioxide, you need to find this plateau here, which is fixing the growth rate. This temperature interval. Well, after having established this window, so you are now safe in the growth process. You can operate your device with certain confidence that you get the same growth rate each time. So usually this titanium dioxide has some oxygen deficiency. Almost all of them have oxygen deficiency. In our case, we have a value about 1.8 for this X in the titanium oxide formula. So it's in between 1.6 and 1.8. So after determining all these process parameters, we started looking at the electronic properties of these structures. So we fabricated some test structure, as you see here. And here, this is a kind of MOS structure, metal oxide semiconductor. Here we looked at the capacitance, voltage characteristics, also current voltage characteristics. So all these things were published in this paper. If you like to know more, so you can check this paper from our group. So of course, the CV curves are just like expected from an N-type substrate. So we have the accumulation type of accumulation-like capacitance curve for the positive voltages, and inversion-like curves for the negative voltages. And there is a strong frequency dependence for the positive voltages, which is showing that some electrons are stored in the structure, and the storage time is compatible with the frequency of the signal. So the reaction of these charges are very much depending on the frequency of the measurement that you use during the CV measurement. So this is quite expected. So the electrons are somehow stored in the at the interface, either at the interface states or in the bending quantum well structures. So an interesting measurement was IV measurements of these materials. So here we see a standard rectifying junction type results. So we have high current for the positive voltages and less variation for the negative voltages. So it means that electrons can flow very easily from silicon into titanium dioxide, but the charge carriers are blocked or less mobile for the negative voltages. So this is proving that titanium oxide layer is an electron selective layer on N-type silicon. So it's a good indication that titanium oxide is, I mean, when we look at here in this Venn diagram, here titanium oxide is here, silicon is here. So electrons can move through the junction very easily because we have a small barrier here and a small quantum well here, so that it doesn't form a strong resistance against the current flow. However, we have a large barrier in the valence band so that the electron holes cannot move very easily from one side to the other side. So these measurements have proven that titanium oxide is a good electron selective layer. So later on, we looked at the passivation quality of ALD grown titanium oxide with chemically grown oxide and without chemically grown oxide. So this is the symmetrical structure we use routinely for the testing the lifetime of silicon. So here on the right side, you see that the lifetime and the implied VOC values as a function of thickness of the titanium oxide layer. So you see, we have obtained very, very good results for the samples with chemical oxide interlayer and also with forming gas annealing. So some hydrogen introduction is helping the structure to improve the passivation quality. So we have reached lifetime values close to 2.5 millisecond. So the implied VOC values are correspondingly improved with the interlayer deposition. So we have obtained values closer to 700 milliwatt, which are very good. But unfortunately, we couldn't fabricate solar cell with this device because our ALD system has not broken after these experiments, and we are waiting for the repairment of this device. Okay, so I have already mentioned that impressive effective lifetime was obtained with 3.5 nanometer thick titanium oxide layer. Okay, well, for the conclusion for this part of my talk, we have analyzed the use of molybdenum oxide and titanium dioxide for the electron and hole selective layer for the heterojunction solar cell technologies, and we see that molybdenum oxide is very promising material. We fabricated solar cells using that, so we can avoid doping, we can avoid use of toxic gases, and these materials can replace the doped amorphous silicon layer in the heterojunction technology. Okay, from now on, maybe in 10 minutes, I can talk about some studies on the standard heterojunction solar cell work at GUNAM. So as you might know, the fabrication process for a standard heterojunction solar cell is quite simple. You see the process flow here. After texturing, surface modification, and after standard cleaning, the deposition of thin amorphous silicon, intrinsic amorphous silicon is done on both sides. The thickness is around 7 nanometers in our case. And one side is coated with N-type amorphous silicon, the other side is coated with P-type amorphous silicon. And on top of these amorphous layers, we deposit metal oxide or indium tin oxide layer or zinc oxide instead. And finally, we print silver fingers on both sides. Okay, well, let's now look what we have done at different process steps for different processes in this technology. One of them was about surface texturing. In standard solar cells today, random pyramids are used. In all solar cells in the commercial market, you can see these pyramids if you look at them by electron microscopy. But it was shown that these inverted pyramid structures are much better in terms of light reflection. However, these periodic structures are very difficult to form because you need to use photolithography, which is very expensive and very slow technique. And also black silicon can be used. Well, there are some studies focusing on black silicon, but here these type of surfaces suffer from the extensive recombination on the surface. Okay, when we compare these three approaches, we see that random pyramids are always good. We have good passivation, good cost, and simple. The other two techniques are not that attractive, even though, I mean, we have very good reflectance. Black silicon reflectance can be down to 1 or 2%. The inverted pyramids reflection can be down to 10%. But we, in our center, we developed a technology which is based on copper-assisted etching. This is a metal assisted etching, actually. And here we form this inverted pyramids on the surface by using a chemical rather than a lithographic process. So there is no lithography here, and we can reach extremely good surface structures on the surface by using this copper-assisted etching. Here, this is our record. I mean, we have achieved 2.6% reflection from the surface by using this tetragonal star-shaped inverted pyramids prepared by copper-assisted etching, which is very promising technique. So we hope to use this in our different solar cell structures in the near future. Okay, next, I mean, the deposition, of course, we studied the amorphous silicon properties in a very detailed way through the years, and we have now established an optimum situation, optimum process conditions for these layers. And recently we looked at this TCO layer, transparent conductive oxide layer, we used on both sides, and also screen printing on top of this one. And let me go a little bit faster. So we have shown that by using reactive sputtering instead of standard sputtering, we have been able to improve the free carrier absorption. It means the parasitic absorption, and then we have improved the external quantum efficiency, as you see. So without any reactive sputtering, So we have this black curve, but with the oxygen, some oxygen partial pressure, we have improved the external quantum efficiency values. We have improved the short circuit current with 0.5 milliampere per centimeter square. So this was another improvement in our heterojunction technology development. But later on, we looked at the use of silicon carbide on the front side, because silicon carbide has a higher band gap. So it means that we decrease the parasitic absorption on the front side. Okay. So we tried to find the best process conditions for silicon carbide. And finally, we have reached these values. So we have reached an efficiency about 20% with silicon carbide. And you see clearly that the blue part of the spectrum, that means the front side of the solar cell was very much improved by using silicon carbide. So the short circuit current was then improved by 0.15 milliamp per centimeter square. So the best efficiency, where best solar cell is shown here from our heterojunction, standard heterojunction solar cell studies. So we have reached the values above 21%. The VOC value is quite high, but however, we can still improve this to higher values. So we hope to reach values like 23, 24% very soon, because we know how to improve this VOC and how to improve this JSC and fit factor. So this is the point that we have now reached at GUNAM in the silicon heterojunction solar cell technology. So, okay, conclusions in this part. Different solar surface morphologies were achieved by copper-assisted etching. So there are a lot of details here, but I didn't put them here in this presentation. But if you like to know more, so just send me an email. I can send you more information. Here, these inverted pyramids can be formed by using copper-assisted etching, and relatively low reflectance values were achieved easily. So we have reached a value of 2.65% of reflection from such surfaces. So silicon carbide introduction was good for the front side of the cell. So JSC was improved. Then ITO was improved by reactive sputtering, and an efficiency about 21.5% was achieved with these improvements. I think that's all I want to tell you today. If you have any questions, just please ask, and I can try to answer your question. Thank you very much for listening.
Thank you very much, Professor Raşit. We will go to Ustad Salim. Are you there?
I'm there.
Okay, thank you very much. So we will, I think we have the floor is open for the audience. And if there are any, so I think I let Ustad Salim behind the scene, he can manage this.
Thank you, Professor Raşit Turan.
Thank you.
I enjoyed the lecture, mashallah, a lot of information and good practice that is done, and experiments for that. So let's move and check who wants to participate, or he has any comments or questions. Please, who wants to ask or who wants to give a comment, you can raise your hand, and you can write in the chat also. Yes. Any questions?
If there is any, No one I would like to ask.
Yeah, I see nothing.
I have a lot of. Very,
Okay,
the-
go ahead, Professor Ahmed.
okay, the first one is in your part where you just took silicon in sandwich between two layers. One is p-type and the other is n-type, which has to be very good in terms of work function, etc. Is that a kind of donor-acceptor concept, or is something else? That's the first.
You mean this?
So you create electron and holes, and then you collect it.
Yeah,
There
sure.
is now heterojunction, there is now homojunction, there is nothing. That's what I understand.
No, I mean, on one side we have a material. We still have the heterojunction, but not doped amorphous silicon. It's a different material, but
Different
still
material.
we have the heterojunction. On one side we have molybdenum oxide, so holes are moving towards molybdenum oxide. Electrons are repelled. They are now reflected from molybdenum oxide. On the other side, we have titanium dioxide. Titanium dioxide is good to collect electrons.
Yes.
But again, we have the heterojunction, but these heterojunctions are not made of amorphous silicon.
Yeah, okay.
And there is no doping.
Okay.
So
So
we have no doping, we have pure materials.
So my question is, you will not go further of the theoretical limit, the Kaiser limit, is it?
No.
This means you can have as at maximum, if you improve everything, 30% maybe.
I mean, in practical cases, you can get about 29 or so, and you cannot go about 30%.
Yeah. Okay, that's one question. The second question is, when I saw your work on heterojunction, like EMIC, like disons, EPFL, the main problem or the main motivation, in my opinion, is the temperature coefficient. You can play. You can make engineering. You can play with different things in order to have a temperature coefficient as low as possible.
Yeah, sure.
And because you have a big market in the desert environment, there are a lot of countries. They have the temperature which is at least 50 degrees in the field.
Yeah.
But here, if you succeed to have this kind of solar cell, you cannot play very much for the temperature coefficient, is it?
No. Temperature coefficient is, of course, related to the energy differences. So that is probably not possible to change much.
Yeah. So which market you are targeting with this kind of solar cell? Is the price will be very low? It's something else?
But heterojunction technologies are offering high efficiency. This is one reason. High efficiency, low temperature coefficient. Yes. Of course, two major advantages. However, the cost of production is still high. Cost of production for heterojunction technologies is still high, even though, I mean, the efficiency is now about 25% in some companies. They cannot sell their product because of the high cost. Still, people are trying to reduce the cost. This is one of the motivations of many studies right now. When you look at China, there are many factories now, heterojunction cell factories, but none of them are successful in the commercial side. This is a big problem. So what market we are targeting? So there is no, at the moment in Turkey, there is no heterojunction solar cell manufacturing factory. There are some standard PV cell factories at the moment, but not heterojunction, just like China. I mean, we have the same situation. So, but we believe that this technology will be important in the near future because we will somehow lower the cost and make it more affordable for the people and more attractive for the PV installations. So of course the main market, I mean the Middle East and North Africa, are of course important for this technology because, as you mentioned, you have high temperature, so these type of cells are doing better in the hot climate. So that can be the target market.
So you think you will get less price as aluminum field based, the standard one, the standard solar cell, what we have in the market?
No. I mean, the most important technology is, you know, PERC type
yes,
of solar
yes,
cells.
Yes, yes.
And it's I mean, it's slightly changed version of standard technology, so it's some improvement. The efficiency is around 22% in the PERC industry today. So if the heterojunction cost will be lower than PERC technology, which is quite possible, I mean, by studies, by looking at different materials, etc., then it might be possible that heterojunction industry is improved. But as you know, I mean, today in Europe, there are two major investments on heterojunction silicon solar cells. One of them is in Italy, in Sicily. There is a manufacturing site. The other one is in Germany. Right now, the Meyer Burger is now building a new factory in Germany. They will make modules like Panasonic. They will make modules with their heterojunction technology.
Okay.
So we don't know yet. I mean, we will see altogether. I mean, which one will at the end will win this race. There is a competition, a race.
Okay. Last question, a very short one. One of the problems is the p-type material. You know, it's very easy to find in type material like titanium oxide. There are others, but p-type material is really a very tough job. Do you think you can find a good p-type material which is good in work function, and also the conductivity can be good?
Yeah,
because
okay.
oxide they have a very low mobility.
Yeah, sure. But molybdenum oxide is quite promising. Its conductivity is not too bad. So I think molybdenum oxide is the best candidate right now. I mean, the alternative is p-type amorphous silicon, as I mentioned. P-type amorphous silicon is not easy, and it's quite how to say, dangerous to deal with deborane and gases. So instead of using p-type boron doping of amorphous silicon, molybdenum oxide is really promising. So I'm expecting this material to be some industrial material very soon.
Okay, thank you very much. Thank you. So
how is it? May I ask you a question? How is it going with the iridescent system? This heterojunction
I saw the executive director with us. I don't know if he's still there. He can answer directly.
Badr
Eken.
Badr,
are you here?
Here?
Are you here? No.
Okay. He sent me a message.
Yeah. So if you are talking about the project what we discussed and we have made a workshop regarding the cluster. They are struggling now to complete this cluster, where some part, for example, to move the substrate from one place to the other. There are many small problems. You know, the technology is from Korea. And we are more close to Europe, and very difficult to have, you know, everything coming from Asia is a technology which you have to be very careful. So I believe that they are working on it. Of course, they have a problem of manpower. Maybe we can have a kind of webinar to discuss with the Department of Photovoltaic there to see what we can do from your side in order to move forward.
Yeah.
But
right now we are planning to order a new tool from you know, Indiotech from Switzerland.
Yeah, okay.
We will have another cluster unit in a year or so.
It's not
Which
this
is,
this Octopus or
Octopus,
something?
yeah,
Octopus,
yeah,
yeah, I
yeah.
know this company because
So-
we want to buy from them something when I was in Qatar, but I don't know what's happened afterward when I left.
This company is still active, so we hope to.
Yeah. They are
hope
very
to-
good. They are very
Yeah,
good.
we haven't reached any agreement right now, but we are talking with them. If we can reach an agreement, we will buy a new system so that, I mean, we will have two clusters in the same building, so that can be good
But
for
they
us.
are expensive. They are very expensive. 3 million and above. Is it?
No, it's not that much.
9?
It's
Because last time
it's
it
about
was-
1.5 million euro.
Yes, something. And all they are very advanced in terms of flexibility and so on. But still very, very expensive. Okay, thank you very much.
Okay, thank you.
Okay. Ustad Salim,
I think
take the floor.
no questions for time being. I think the discussion between you, Mr. Akisu, if you want to give any comments, the floor is there. You can have yours. It is open. You can talk if you.
Akisu?
Akisu, yes.
Akisu, yeah.
Yeah.
Axisu.
Axis.
Aksisu.
Okay.
It's okay. I think we finished. Just let us thank you, Professor Raşit Turan.
Thank you. Thank you.
Let's give for tomorrow. You are there. You can open your microphone, please. Welcome. Hassan Mubarak. All right.
I don't think that he's interested.
Okay.
Yeah.
So let's
so
for tomorrow. We are having at 11 Morocco time with Dr. Jamila Murabit. The title here in Arabic it will be her lecture سياسات وقوانين الطاقات المتجددة. So inshallah this is it will be the day 8 tomorrow. Hopes to see you tomorrow inshallah. Thank you, Professor.
Thank you.
And thank you, Professor Ahmed. And thank you for all the participants and the members also. See you tomorrow, inshallah.
Thank you. Bye-bye.
Thank you very much, Professor Turan.
Bye-bye.
Thank you. Bye-bye. Bye-bye.
Bye-bye.